The title of this talk is Thermodynamically Possible Order Formation Excludes Evolution. It will describe the second law of thermodynamics, which says that in any isolated system all natural processes move from order towards disorder and never vice versa. In open systems, however, certain kinds of limited order formation are possible. Nevertheless, it will be shown that the hypothetic process of evolution does not belong to these open system exceptions. It is therefore excluded by thermodynamics. That means it does not belong to reality. To understand the universality of physical laws, it is important to know that all matter is composed of the same kinds of particles. From galaxies to the Earth, from stones and water to metals and also the bodies of living creatures. Every material thing is built up of molecules and atoms, which in turn are composed of protons, neutrons and electrons. If we want to know the physical behavior of material objects, we only must know the physical laws that govern the atoms and molecules in them. The two most important laws governing the behavior of physical objects are the first and second law of thermodynamics. The first law, the law of energy conservation, says that in any physical or chemical transformation, the overall energy can only be changed from one form into another, but never be destroyed, nor can energy be produced. The second fundamental law, which is particularly interesting for the following considerations, is the law of increasing entropy. It will be explained in the next slides. The second law of thermodynamics can easily be understood at the example of a system of particles which move randomly in all directions. For example, a set of gas molecules in a closed volume. The velocity with which they move defines the temperature of the gas. In this so-called Brownian motion, the molecules are colliding with each other permanently. In each random collision, they change their velocity and their direction. As a result of these random processes, the particles will be homogeneously distributed in the available space. Similarly, their average momentums, that means in the case of identical particles, their average velocities, will be the same. With other words, the temperature will be homogeneously distributed. This temporal behavior of any set of particles is illustrated in the next two slides. The volume at the top shows a gas with an ordered temperature distribution. The slow, that means cold molecules, are in the left half of the volume. The hot, that means the fast ones, are in the right half. As a result of the random collisions, at any time later, the whole system will have moved towards a more homogeneous distribution of momentum or temperature. Finally, it will be a completely disordered distribution of particles as shown in the bottom image. This state is by far the most probable state, while it is highly improbable that the molecules are arranged in the ordered manner of the upper picture. If the transformation proceeded in the opposite way, from the probable to the improbable distribution, it would not necessarily change the overall kinetic energy of the system. That means it would not necessarily violate the first law of thermodynamics. However, the second law of thermodynamics prohibits such a transformation from bottom to top, simply because it is too unlikely. The same is true for a system with an ordered distribution in space. with increasing time, the molecules will distribute more and more homogeneously over the entire space. The system will move from the ordered configuration in the top image to the disordered configuration in the bottom image. That means from a state of low probability to a state of high probability. Again, the opposite transformation, although in accordance with the first law, is excluded by the second law of thermodynamics. The disorder cannot move towards order. This universal behavior of the entire material world, as described by the second law, has been formulated in a precise mathematical terminology by physicists. The central quantity is the entropy S. It is a measure for the probability P of a state of a system according to S is equal K times logarithm P. The higher the probability of a configuration, the higher is its entropy. In principle, this probability, that means the entropy, can be calculated for any material object. The textbook formulation of the second law of thermodynamics for any isolated system of matter is given as this. A system will never change by itself into a significantly less probable state. That means its entropy will never decrease by more than a few K. The allowed fluctuations by a few K, that means a few times the tiny Boltzmann constant, are negligible for our considerations. This law is the basis of the entire nature and well known to everybody by our common everyday experience. This statement of Lieb and Ingvarsson in the journal Physics Today emphasizes the important role that the second law is playing in the universe. No exception to the second law of thermodynamics has ever been found, not even a tiny one. Like conservation of energy, the first law, the existence of a law so precise and so independent of models must have a logical foundation that is independent of the fact that matter is composed of interacting particles. A few macroscopic examples of the way in which the entropy law governs our world are illustrated on this page. Everything is moving from order to disorder, but not vice versa. A mixture of two liquids with similar density but different color will proceed towards a homogeneous, disordered distribution. The opposite process, that the homogeneous mixture demixes itself, is excluded by the second law, because that would decrease the entropy. Equally, a solid body like a house will, by the random impact of sun, wind and rain, be transformed into a ruin. Yet it is impossible that these random forces are restoring a ruin. Finally, genetic degeneration of a biological species due to negative mutations illustrates the effect of exposure to thermodynamic forces. An example of such an information loss is the blind fish Astyanax, which is living in dark caves where eyes are not necessary. From outside, no parts of eyes are visible, although inside the head some fragments can still be observed. Therefore, we can conclude that this kind once possessed completely functioning eyes. A succession of micro-variations led to the destruction of these complex organs. This is a natural process of increasing entropy. the opposite, that a long succession of small genetic variations and selection eventually leads to the construction of a completely new organ, is an excluded process of decreasing entropy. Often, at this point, it is objected that the second law refers only to isolated systems. Our biosphere, as well as every biological creature, however, are open systems. That means they can exchange matter and energy with the surroundings. Therefore, it is argued, the transformation of disordered molecules into ordered biological organs is not prohibited by thermodynamics. To check whether this is true, it will now be examined in detail which particular kinds of order can form in an open system, and whether biological order is part of them. This slide illustrates how the import of energy into an open system can indeed produce order, that means decrease the entropy. Nevertheless, we can see at this and the following examples that such a production of a very limited kind of order is only possible if certain preconditions are fulfilled. The left rectangle represents a volume of air which contains a smaller volume within. The whole arrangement has a homogeneous distribution of temperature of 20 degrees C. It is a state of disorder, a state of high entropy. If the smaller volume is the inner space of a refrigerator, then the import of electrical energy from outside will cool down the air within, while it will warm up the air outside the refrigerator. In this way, a low entropy temperature distribution is produced, 4 degrees C in the refrigerator and 25 degrees in the room. Order has emerged apparently only by the import of energy into the open system. Yet it is not alone the energy. Without that complex mechanical construction of the refrigerator, the process would not have taken place even with an unlimited amount of energy. The presence of an order-producing machine is prerequisite, a machine which already contains a program for converting the undirected energy in such a way that a low entropy distribution results. Therefore, such a process does not give rise to any new information. Everything was already contained in the machine. Living beings are further examples of open systems which can produce order if energy is supplied. When the sun is shining, green leaves convert carbon dioxide and water molecules into oxygen and complex carbohydrates. Disordered small molecules, representing high entropy, are transformed into ordered large molecules, a state of low entropy. Again, this entropy decrease would never take place even if the entire energy of the sun were available, unless a complicated photosynthesis machine pre-exists in the chloroplasts of the leaf. It must already contain the program and the information for the order to be produced when the energy is switched on. Nothing new emerges. Another category of entropy reduction by energy exchange is the formation of crystal structures when heat is exported out of an open system. Water molecules, for example, will slow down their disordered random movements when they are cooled. Due to the directed interatomic forces between them, they will at one temperature stick together and form a perfect hexagonal crystal lattice. It is energetically favorable for them to arrange in this way. The accumulation of many such hexagons results in the formation of a crystal with a six-fold symmetry, as we can observe it in the snowflakes. We must now ask, is it enough to export energy if we want to obtain such a complex order out of disorder? The answer is no. The symmetry of the H2O molecules and their directed interatomic forces must already exist before. Otherwise, the most extreme cooling process would never deliver an ordered structure. Therefore, the order information is already present before the process starts. The visible crystal symmetry is pre-programmed in the molecules, which simply move into their state of lowest energy, a state which is defined by the H2O geometry. No new order or information is produced by crystallization. The final category of order formation by energy exchange are the so-called dissipative structures. The photograph shows what happens in a pan of oil when it is heated above a certain temperature. Characteristic ordered cells emerge out of the disordered liquid, which are called Bénard cells. Further such examples are the vortex in a tornado, a standing wave in a flute, or oscillating chemical reactions. In all cases, energy is dissipated in a way that stable ordered structures appear. If we regard the cross-section image of the Bénard cell, we can explain the phenomenon. The heat energy from below is transported to the colder surface above via stable convection cycles in the oil. They are stable because an increase of their velocity would result in a larger energy transport. The upper surface would therefore get hotter. This, in turn, would mean a reduced temperature difference between the two surfaces. Since this difference is the driving force for the convection, it would slow down again. Then, however, the temperature difference would increase again and the convection would accelerate, and so on. With other words, any deviation from the stable cycle results in a force that drives the system back into the stable state. This is simply a resonance in a feedback loop. We finally arrive at the same conclusion as with the other examples. It is not enough to import energy. As a prerequisite, a feedback mechanism must exist before, a mechanical or physical arrangement that already contains the information for the order that will become visible at a certain point. In contrast to the categories of complexity discussed so far, biological order may be described as specifically complex order. That means such a complex order, like the DNA or a wing, which represents a specific functional or aesthetic organization. The important difference is that biological organs represent new information. This one is not pre-programmed in an ordering machine. It is also not pre-programmed in the geometry of the constituent molecules. That means it is not energetically favorable for molecules to arrange in the form of a living creature. Finally, it is not pre-programmed in a feedback loop either. Therefore, we are led to the following conclusions. The law of thermodynamics demands that material order always turns into disorder, and never vice versa. In open systems, the exchange of energy allows for certain categories of exceptional limited order formation, which is sometimes called self-organization. However, it does not organize itself. It emerges only if the structural information has been organized before the process starts. Such a machine, a molecular structure, or a feedback loop in which pre-existing information for specifically complex structures of biospecies is organized, does not exist. The hypothetic process of evolution claims that disordered molecules can eventually turn into specifically complex order. Therefore, this process does not belong to the open system exceptions. It is thermodynamically excluded. The result of this examination is that the evolutionary theory is in contradiction to the second law of thermodynamics, which is the basis of nature. Therefore, it does not belong to reality.